Introducing BhuVargikaran, an automated system for land use classification of satellite images. Do you know there are around 5,000 satellites revolving around the Earth? Have you ever wondered what happens to the satellite images sent back to the Earth? How can we extract invaluable information from these images? But most importantly, why? Every minute, images are sent back to Earth. Currently, there are two different common methods to do this task. These images are manually classified by individuals, which lead to inefficiencies and human-prone errors. Or these images have to be analyzed and classified over different softwares, which leads to issues of interoperability and slow responses. We propose an all-in-one system that can resolve all these issues and handle real-time dynamic data in seconds. We focus on data-driven decision support system. The model is feedback-based, so the model can learn and perform better as it is used according to the need. The model is trained over and hence can work with different resolution satellite cameras. Using our system, it is possible to predict how regions are going to shape up in future and land usage-wise based on their past and current land use. We have paid significant attention to make our model light to carry on all devices and scalable to absorb rapid incoming data. But why do we need this? First, for future planning of any region or country. Understanding the current scenario of how the land is utilized and comparing it with past, we can plan for the future. Example, if the surrounding areas have been barren for years, the green stretch beside it may also turn barren, so it is better to set up industries there. Second, protecting endangered areas. Satellite images provide us with data through which we analyze the stretch of forest land over the years. Unsurprisingly, deforestation is very apparent. We can revive forests to reinforce a stable environment and balanced ecosystem by finding suitable areas away from human-occupied regions. Climate change. Do you know that Arabian Sea is slowly but surely entering into the land through western coastline due to rising sea level? Our results prove this phenomena. We have also found increasing desert areas in the northern region of the country, all pointing to serious climate changes. Agriculture. It is easy to monitor and do surveillance on large agriculture fields. Officials can analyze the quantity of the production. For example, for long paddy and sugarcane fields where the appropriate water is reaching, finding the water stress, diseases on the crop, the amount of produce, etc., where frequent visits to field by farmer are not possible. Immediate and urgent actions can be taken. If flooding happens or there is a forest fire, apart from alerting, we can also find source and analyze the damage automatically. We can continuously monitor forest cutting and damages and generate reports on regular basis. Our model also handles drone images, and the light interface can be shared with stakeholders like farmers, government officials, etc. BhuVargikaran contains three major sections based on functionality. Annotations on satellite images denote information regarding the classification of their land use. Multi-class classification, since a particular tile image may contain multiple land use types, we employ multiple and percent-wise classification. Temporal classification is important to analyze how land has evolved over years in order to predict the future. For multi-class classifications, we have taken 10 classes of land cover. For each satellite image after grid cutting, we will try to analyze and respond all the classes and the percentage covered by them. Off to the applications. Industrial planning. Having a major inhabited land and a water resource nearby can be beneficial for industry and permits can be given. Threat detection in cases of forest fire detection or monitoring the LOCs and LAC control borders to recognize territorial activities. Agriculture. Apart from crop, the previous use cases, we can find suitable areas for particular crops based on previous crop, nearby water resources, etc., and then decide which crop to grow. And lastly, for conservation of ecology by keeping tabs and reports on natural habitats. We have utilized data set from ISRO's website BhuVargikaran. We have made our model scalable and flexible using image generators and placeholders respectively. To make our model light, we have utilized TensorFlow Lite, and the model can be deployed on all the different devices. Annotations. In annotations, we have used semantic segmentations and assigned labels to each pixel and grouped likewise. We have used DeepLab V2 and V3 for semantic segmentation because heterogeneous convolutions helps us to enlarge the view of filters without increasing parameters or time of computation. ASPP has further improved our accuracy by accounting for different object scales. Temporal classification, analyzing changes over time for a particular region of interest and then further predicting future land use. This can be done to analyze, detect, and quantify the impact of climate change like rising sea levels, droughts, and decreasing freshwater resources. We can utilize this data to prevent upcoming hazards. Urban development planning alongside taking appropriate measures to coexist development with conservation of environment. And all this can be utilized to predict the most probable future for a particular region. Increasing industries in a region signify for a future of more employment and hence more residential areas and less farming. We have also accomplished the future of providing the stakeholders with the most ideal plan for a region using predictive analytics based on earlier application statements which can be altered according to need. The plan is created keeping majority of the important constraints in mind. Stakeholders can tick off the constraints they do not require to get a transformed and a new plan. To check the prototype of our application, BhuVargikaran.pythonanywhere.com. You can upload any image with any format in order to test our prototype. You can also download images from above. In order to input those images, just click on the upload image button and submit the image. You can see a preview of the image. The image is in 28 pixels format. The percent and the multi-classification is given for that particular image. The image that we had taken was from pasture category. As you can see, since pasture is related to annual crop and forest, there is a small percentage that it is showing as annual crop and forest. Let's try for Mumbai 2008 satellite image. So we have some percent in multi-classification of the Mumbai's image. Forest 15, Sea Lake 35, Industrial 10, and Residential 15. We will compare this with the Mumbai's 2017 satellite image. Let's try now for Mumbai's 2000 satellite image. This is Mumbai's 2017 satellite image, which we are submitting now. As you can see, there are some differences. We will note these differences down. So Forest 8, Sea Lake 35, Industrial 16, Residential 17. Let's compare this with the Mumbai's 2018 analysis that we have conducted. So well, decreasing forest, check. Increasing sea lakes, The percentage of sea lakes is very less, therefore we have 35 constantly. Increasing industries as well. Let's see a demo for temporal classification grid cut 2008 2017. You can see the change map and the clean change map that denotes the changes that are taking place over the images. So the inferences that we can gather from this analysis is that there is a rising deforestation in Mumbai region, increasing industrial and residential areas, which is quite apparent. Annotations, change map, and ideal map will be uploaded on the website for use from August end. As Abraham Lincoln said, the best way to predict the future is to create it. Thank you for patiently being with us. Please check our website and continue supporting us.